Okay, in this one we're going to be talking about using diffraction patterns and double slits and single slits and things like that in order to manipulate our light source, like with the sodium vapor lamp, or get a laser pointer to interfere by going through diffraction gratings. Now, if we go back over the last video, I had these sorts of things on the board, and there was another pair where stuff was completely out of phase. Now, in order to arrive in phase, the waves need to be doing the same thing at the same time. So they need to have come from the same point, the same light source originally, and be propagating outwards and end up doing the same thing at the same time. Now, it doesn't have to be that the same wave front meets up with the other ones from the same place and time. So it doesn't mean that they have to both take 25 steps to get there. It could be that one of them takes 24 steps and the other one takes 25. All right, as long as they have a whole number of wavelengths that they're out by. So the wavelength is the step. Whole number of wavelengths that they're out by, they'll arrive at the same point doing the same sort of thing. One might have travelled a bit further than the other, but that's okay. It'll still be peak on peak, trough on trough. You used to get constructive interference. Conversely, though, if we have this half a step out of whack, we're going to end up with a peak landing on a trough or a trough landing on a peak. So it might be one wave takes 25 steps, the other one takes 24 and a half to get to the same point at the same time. And that would mean that one of them's kind of half a step off or completely out of phase with the other one. So you'd get perfect destructive interference. So this would be destructive and this would be constructive. So in terms of light, we're looking at an increase in intensity here and effectively no intensity of light here. So what I've got drawn up on the board at the moment is a screen over here. So this would be what you're actually looking at on, say, the whiteboard or the screen on the Young's double slit experiment, where you would have bright and dark spots across the screen, and over here I've got one light source and here I've got another light source. So these are they arrive at this place here, so this is going to be a double slit in this example. They arrive at this double slit in phase, so we've and coherent, so we've made them oscillate in the same direction, they are the same colour, they arrive, they're doing the same thing at the same thing at the same time. So one of them is going to take path 1 to get to A, the other one is going to take path 2 to get to A, and it just so happens that one of them is going to have a whole number of wavelengths further to travel. So you can see this one is a little bit further. It's going to be a whole number of wavelengths further to travel than for path 1, and what that means is the path difference between the two. So usually it'll be OPD, so the optical path difference is a whole number of wavelengths, so we're going to get constructive interference at that point there, right, at A. Now at B is supposed to be in the middle, and it's pretty close. So you can imagine that if we went from this point here, or so point 1 to B and point 2 to B, they would end up going the same distance, the exact same distance. They would meet in the middle, so the optical path difference there would still be an integer number of wavelengths. It's just that the integer would be 0 in this case, so there'd be no difference whatsoever. C is meant to be the same distance from B as A, so same kind of deal. It's just the light coming from 1 has had to travel a further wavelength than the light coming from 2 in this case. So we still have this optical path difference of a whole number of wavelengths. Now, right in the middle of these two spots, we're going to have the destructive interference. We're going to have these points right here and right here where we're going to have negligible 0 intensity. And that's because our optical path difference is some lot of a half wavelength off. So it might be half a wavelength, might be 1.5, might be 2.5, might be 78.5. Doesn't really matter. If it's half a wavelength out, then it's going to be destructive interference. Alright, so one way that we can do that in the lab is by getting a sodium vapor lamp, which is yellow light. Yellow light is from the sodium vapor. The vapors are oscillating, vibrating in all different directions, and when they're doing this, they're giving off the electromagnetic radiation in all different directions. So in order to, so you can see it's kind of scattered here. So in order to have it sort of, be doing what we want it to do, we have a vertical slit that we make all the light go through. So if we have a vertical slit, only the light that's oscillating vertically can actually get through there. Any light that's going sideways or diagonally or whatever it is going to get blocked out. It's only the stuff that's going perfectly vertical that'll be able to go through that. And once it goes through that, we're going to get it to hit a double slit setup just like this one. The light has come from the same source over here. It is in phase, it is coherent, and when it hits these two, it's going to do this, sort of wavefront. See if you can imagine, sort of do this propagate outwards like this, and you're going to end up with peak on peak up here and here and here, and then and trough on trough, and you're going to end up with peak on trough arriving here, and I guess up there and down there. Alright, so when it's constructive interference, whole number of wavelengths. When it's destructive interference, it's a half, 1 m plus a half wavelengths out of phase.